Alright, so today I'm going to be explaining another important article on graph representation learning. And the title of this paper is on information dropping and oversmoothing in graph neural network, which is published in ICLR 2024. So graph neural networks are widespread in graph representation learning. Random dropping approaches, notably drop edge, drop message, claim to alleviate the key issues of overfitting and oversmoothing by randomly removing elements of the graph representation. Of course, there is a paper that says drop message is more general than any other dropping methods. So, however, their effectiveness is largely unverified. In this work, they show empirically that they have a limited effect in reducing oversmoothing at test time due to their training time exclusive nature. And we show that drop edge, in particular, can be seen as a form of training data augmentation. And its benefits to model generalization are not strictly related to oversmoothing, suggesting that in practice, the precise link between oversmoothing and test time performance is more nuanced. We additionally address the limitations of current dropping methods by learning to drop and propose a new information theoretic approach, which performs dropping during message passing by optimizing an information bottleneck. So we also observed that enabling random dropping at test time will considerably reduce oversmoothing. So dropout is introduced in 2014, stems from the notion that the random deactivation of certain units during training equates to training an ensemble of networks. And this process effectively counters overfitting in various models. Drop edge in 2020 adapts a different strategy by randomly omitting a subset of edges. Many earlier works on oversmoothing have proposed practical techniques, and recently people talk about oversmoothing still because it's a problem, fundamental problem. So the contributions there are many contributions in this paper. So first they talk about measuring smoothing, that in the literature they use mean average distance, MAD, the mean average, which I discussed in the previous video. Also in the previous video I talked about Dirichlet energy, which is more recent, relatively recent in the oversmoothing literature for as a measuring smoothing measure. So we specifically investigate methods that inherently scale the embeddings. We also consider using MAD, which has two known limitations. First, complete oversmoothing, all node representations being identical, does not equate to zero MAD. And it is ineffective in the case where the node representations are scalars. Nodes with the same sign but different magnitude cannot be distinguished. However, it can still be shown that for multidimensional MAD, there exists constant, so that we can bound the MAD like this. And then they did some experiments. So the overall idea is to seek a representation Z that is minimally informative about the input X input X, representation Z. We want and simultaneously we want to maximize mutual information between Y and Z, the output. So recall that in message passing, a layer L can be updated like this. We call this aggregation, we call this phi the update. And different psi and phi, you have different methods for graph neural networks. Of course, all of them are very local. They suffer from over squashing and all of these things. And but the idea of this paper is very interesting, that they just balance mutual information between X and Z and Y. So what they want is, first X, we have a latent variable Z, and we have our label Y. So we want Z and Y, these two, we want to maximize mutual information, very dependent to each other. On the other hand, we want to reduce this mutual information, because otherwise your oversmoothing is everything is just a copy of that. It's very dependent on each other. It's not trying to learn something from very remote nodes. So it is also good for over squashing to some extent, very locally, of course. That's why this paper didn't talk about over squashing, because it can handle it, but very locally. So these two can be written like this: information bottleneck principle. We know that we can obtain it like this. And we have parameters theta and phi to be able to do this. So we use a variational approximation. It's very hard, so we approximate it. For example, the first term, Z and Y, this term can be approximated like here. We have a lower bound for that. Similarly, this one, X and Z, we have an upper bound for that. We can approximate it. So just simplify it. You will see that you can have this final objective. We want to maximize Q, log of E, expectation of log of Q, and the KL divergence, expectation of KL divergence between P and R. So the rest of that is just calculations. And the experiments of Cora dataset, Side-Seer dataset, Texas dataset, for different layers. Look, we have experimented on 128 layers. You see, as the number of layers grows, oversmoothing is reduced. The Dirichlet energy is reduced. So we can compare oversmoothing across 6-node classification dataset. So all of these Cornell, Side-Seer, they are node classification. Cora, for each of the nodes of the graph, we want to know what is the label of that.